right. Okay, so let's get started. Couple of comments. So final exam is a little less than 2 weeks away. Wednesday of finals week, I believe. I would like you all, if you could, to look over your schedules, your final exam schedules if you haven't already. And if you do have a situation where you have too many exams on that day and need to reschedule this exam, it's better if I hear earlier rather than later about that. So please do check that and get a hold of me. And we will have one alternative testing time. And so I'd like to make those plans next week. I'll send some announcements about rooms for the final exam as well next week. And just a comment, so this homework this week will be graded as usual. The homework that is assigned next week is lower. I mean, there aren't that many problems, and the grading will be essentially, if you've made an effort, you'll receive full credit. So next week's homework, I just want you to have some exposure to some of the problems, look over them, but it's not going to be graded heavily for accuracy. It's just give it your best try, and it will be. That's how we're taking next week's homework. Okay. So I had an occasion to talk with a student or two since last lecture, and I do want to make a comment that I think may be something people are struggling with this material. I'm trying to emphasize it as I'm going through this, but it's a practical significance when you're actually doing problems to sort of ask yourself a question. Okay. So there's going to be, with the notation we use, we're going to have one of three situations. So if you're faced with an integral, all right, in this class, you're going to see one of these three possible notations, okay? And below it, you're going to see different things, right? Now, those things are important to look at when at this stage in the game. What we're looking at down here is important, right? It's not necessarily one thing, right? So if I look here, one variable calculus, we're used to going from A to B, or we're used to thinking of this as being, an interval, the C to be an interval on the real line. But here in this class, C could be a curve in one dimension. I mean, it could be an interval. It could be a curve in 2 dimensions, or it could be a curve in 3 dimensions. It could be a closed curve. It could be not so closed curve. It could be a disconnected set of curves. So what this is important. It could be an oriented curve. So I want you guys to ask yourself, as you're doing these problems, or when you're confronting these problems on an exam, what is this question asking? Before you jump into computing, ask that question. Similarly here, we have domains in the plane, but now as of last class, we could also be talking about a surface in 3-dimensional space. Okay, so that's a different kind of a thing, and you have to use different techniques when you look at those different domains. And here, we really only have one thing we're actually doing, which will be, some kind of blob inside of 3 dimensions. Now, you can do this more generally, but okay. The other thing I want people to ask themselves when they're doing these types of problems is what goes here? What is in here? Okay. Because we can have one of two things in this class that appears in these two integrals. There are one of two things. We could have a function, f of xy, say, or even f of xyz if we're in 3 dimensions. But I'll just write like lowercase f. Similarly, here we can have a function f. Or we could have a capital F, which is usually, I mean, this is usually written capital F, but it could be written capital G, whatever. With, it's going to be bold in the text, but in lectures, I put a little arrow above it. These are vector fields, okay? Now, if you see an integral and you're faced with this kind of a thing, a scalar line integral, there is a set of techniques and formulas to use. If you see an integral and it's this kind of a thing, there is a different set of techniques to use. Okay? So making that, pausing before you jump into the problem, looking and identifying what is the integrand, what is the domain, it's important. It's not, you can't really succeed at doing the problem if you haven't done that yet. All right, so I just want to go through that slowly, just to emphasize that that's an important thing to do at this stage in the game. Are there questions about this? Except, what is that noise? Very odd. Oh, it's like the one? I don't know. All right. Okay. No questions. All right. Okay. So last time, what did we do? Last time, we did scalar surface integral. And these were things that look like this, where we had a lowercase f in 3 dimensions. Our domain was a surface in 3 dimensions. And we wrote ds. And I won't rewrite the formula. I mean, as you recall, it was, well, maybe, okay, maybe I will rewrite. So one formula we had is if we had a domain D and we had a parametrization given by x, y, z of 2 variables u and v, so D is in the uv plane, we could write out this formula and use it. And here we had this TU cross TV. And here we had DU DV. So this right-hand side was you're going to a domain that's inside the plane, and you can actually, at least in principle, compute this using Fubini and these other methods. So what we want to do today is we want to, just like when we went from scalar line integrals to vector line integrals, we want to go from scalar surface integrals to vector surface integrals. So that's going to be our first goal today, and main goal. We'll touch on Stokes' theorem, but the main goal is to really get to vector line. Not vector line, vector surface. Sorry. So what we needed when we did this with curves was we needed to actually upgrade the domain of integration from a curve to an oriented curve. And as I said at the end of last lecture, we need to do the same thing here. We need to take a surface and have a sense of orientation on the surface. And you'll have noticed, I'm sure, at some point in your life, that when you look in a mirror or something, things like reverse orientation, right? Or if you're like looking at, if you're looking at, say, a glass, and there's someone on the other side, and you draw a clock and you say it goes clockwise, then the other person on the other side of the glass will say, no, that's going counterclockwise. Right? So if I have a surface in 3-dimensional space, the notion of orientation is not inherent. It's actually something that is an extra condition that we have to define on the surface. To say, okay, we're going to give ourselves a notion of orientation on a given surface. So the way we do that, at least with surfaces inside of three-dimensional space, is we specify a continuous normal vector field along the surface. So we need to take our surface and make it an oriented surface. And this means it's the surface with a continuous choice of normal vector. We'll say you might as well make it unit normal vector, and which we'll call n, capital N. So this normal vector is changing as I move around my surface, but it's always normal, it's always a unit vector. Okay. So if I have some kind of a surface, to give it an orientation means that I'm just everywhere giving it a unit vector that points, that's orthogonal to the surface. And it has to be continuous. We don't do some crazy switch somewhere where we just decide to change our orientation. It needs to be continuously changing. Okay. Make sense? Okay. Now, as I said last time, there is this right at the end of last lecture. There is a new wrinkle once we go to surfaces, from curves to surfaces. Actually, surfaces are far more complicated than curves in some sense. There's a lot more interesting things you can say about surfaces. And one of these things is that with curves, if I give myself any smooth, nice curve inside of R3 or R2 or whatever, there is a notion of an orientation of that curve. There are a couple of notions if it's connected, right? However, with surfaces, you may not have an orientation. So you may not be orientable. So let's just make that statement, which is that some surfaces are not orientable. And this is discussed in the text, but just to illustrate this fact, you guys probably have seen, I guess we did this, seen a Mobius strip before. Have you guys all seen this? Such a thing? This is like something in popular culture. So you take a strip and you make, one way you can do it is you take like a piece of paper and then just twist it once and then glue the ends together, something like that. That'll give you a Mobius strip. And it turns out there's no, if I start with a normal vector that's sort of pointing up, then as I travel around, because of that twist, what's going to happen, right? So if, let's say it's pointing out this direction, we see that once I go through this twist, now it's pointing in. And so once I get to the other side, I've all of a sudden reversed my normal vector just by traveling globally around the surface. And in fact, you can prove mathematically that there is no, that's one illustration, but that there does not exist an orientation, a global orientation for this Mobius strip. This is a feature, as I said, this is a feature of some surfaces. They're sort of, I don't know if I want to say they're rare, maybe, but in fact, in higher dimensions, this kind of thing happens as well. So you can define three-dimensional spaces. Who knows, we may live in one, where if you traveled around the universe and you came back to where you started, your heart went to your right side of your body somehow, just by the topology of the space. And it's possible. We don't know really the shape of or the topology of the universe. But such things happen as far as mathematically. And so what we want to do is we want to be able to say, well, if we're going to do these vector surface integrals, we need to have a surface that does have an orientation. So we're not going to be doing these types of integrals on such surfaces. So our input for domains is going to be an oriented surface. S. And let's see what the picture is here for our vector. So let's say this is our S, or at least a piece of our S. Now, we're going to have this normal vector field n at every point. And now we're going to imagine what's our input domain is S, is oriented to S. What is our input integrand? It's going to be a vector field. So we have some background vector field. And we don't really care about that vector field away from our surface. We're more interested in what's happening right at our surface. And if we look locally at a particular, if we look right at a particular point, say this point here, what we're interested in calculating when we're calculating a vector surface integral is a flux computation. We're interested in seeing how much, if we're imagining this vector field as the velocity of a fluid, how much fluid is passing through our surface at any given time. That's what we're interested in computing. So what we do is what we did in the flux integral for a curve. We're going to project and find that contribution of this vector field F, the amount of the vector, amount of the flow of that vector field that's actually passing through the surface, not going tangential to the surface. And so this quantity here, which is this length, that quantity is really just, as it was before in the case for curves, it's just the dot product. Right? And that is because our vector field, our orientation vector field, is a unit vector field. This, let's say parenthetically, this is because this dot product is equal to the magnitude of F times the magnitude of n, which is 1, times cosine of theta, where theta is the angle between them. So since we know the magnitude is 1, this is just F times cosine theta. And you see when you make this triangle, this is our angle theta. Let's blow it up a little. If we're trying to compute this length here, this is just F times cosine theta. So the amount of contribution infinitesimally at that particular point, the amount of fluid kind of flowing through at that particular point is really given just by F dot n. And now if we want to get the amount of fluid going through the entire surface, well, we're going to take a scalar surface integral of this. That's how you want to add these contributions up per unit of surface area. So our vector surface integral is going to be a scalar integral of this dot product. The notation is slightly different. We have this F, although it looks a little bit like the case where we did with line integrals, at F dot ds, S is capital now, but this is defined to equal, as I said, just the ordinary scalar integral of F dot n ds. Oops, no vector here. This is a scalar integral. That's the definition of our vector surface. And what it calculates, again, the meaning behind this, what it's calculating is the amount of flux, essentially, of this vector field through our surface. Total flux. Very physical concept, and an important concept you want to be able to get your hands on. Okay, so this is the idea of it. This is the definition of it. How do we compute? How do we compute? This is the definition. And you'll notice, of course, in this definition, before we get to the computation, We did need this to be an oriented surface because, of course, in the definition is that unit normal vector field that we're dotting with. So if we don't have that, we can't really even define. Okay, but the computation is not very bad. The computation just, all we have to do is take our definition and take our formula that we have up here. So let me bring this down. And I need to say a couple of words before I go ahead with this computation. So let me give myself a little room. All right. So before using these formulas, let me make a couple of words. In order to compute the scalar surface integral, we needed a parametrization of our surface, right? That was how we actually got to computing things. Now, just like with curves, when you parametrize, you can parametrize in a way that's compatible with the orientation or that is anti-compatible, that kind of reverses the orientation. So what we want to do is we want a notion of that. So we'll say I think the book, I looked at the book, the book uses R again, which I'm not a huge fan of, but okay. They use R of U of V. But this is their parametrization of the surface. That this is compatible with orientation on S. So it's parametrizing S. If this vector here, which is indeed normal to the surface, is a positive multiple, we'll just say points in the same direction as M. So if I have a surface and I look at that surface and I take these two tangent vectors, TU and TV, these correspond to two tangent vectors. Say this is TU, this is TV. If I take their cross product, one thing we know about the cross product is that we should get something that's orthogonal to both of these vectors. So we get something orthogonal, TU cross TV. And because it's orthogonal to the surface, it is a normal vector to the surface. Maybe not be a unit vector, probably won't be, but it's certainly orthogonal. And so we can ask, is that orthogonal vector pointing in the direction of n, or is it pointing opposite to the direction of n? If everywhere that we look, it's always pointing in the same direction, then we say that this parametrization is compatible with the orientation. Questions about that? Very quiet. It's always quiet. Okay. So in this case, we know something. We know actually what n is. N is just this vector, but now normalized. Right? We can just divide by so now let's use that along with this. So if I look at this definition, and if I have a compatible orientation, let's assume that. Okay, I'm going to try to give myself a little more room. So this should equal, this is a scalar surface integral. So this is equal to, using this formula that I'm writing it below, this is equal to d of f of x uv y uv z uv dot n. But now n is, as I said, if I have compatible orientation, it's this. Tu cross tv over tu tv. That's this right here, this expression in parentheses is the scalar function that we're integrating. It's a scalar function. This is a vector here. I'm dotting it with another vector here for any u and v. That gives me a scalar. So this is a single scalar. Of course, I have to put my, that's the scalar function. That's my f here. So then in the formula, I need to multiply by tu cross tv, du dv. And you can see, because if you multiply one of the vectors in the dot product by a scalar, you can bring that out. You see that you get some cancellation here. And what that then leaves you with, I'm going to erase this, used it, is it just leaves you with this formula. Integral over d, and now remember, d is now a domain inside of the plane. So you've got an ordinary type of an integral once you work all of this out. And now you're going to dot with this vector, which I think in the book they call lowercase n, but it's some vector, du dv. And as in the case of line vector line integrals, a vector surface integral is much easier generally to compute, or at least you have more hope computing it than you would a scalar line, because you're missing this sort of square root. All right, so this is the practical computational formula that you can use if you're computing a vector surface integral. And I want to say, guys, I know spirits can be low at this point in the course, but this is as hard as it gets. This is it. I mean, this is the hardest type of kind of computational formula that we have. Everything from here on out is sort of ways of making this easier, I would say. Questions? Okay, let's do a problem. How's that sound? Let's do a problem. An interesting problem. So let's calculate the flux, my vector surface integral, of the following vector field. So the vector field, those of you in physics will potentially know. Maybe. X squared plus y squared plus z squared to the 3/2. And see. Well, it's close to something you might know. Or certainly you've seen it before, whether you recognize it. We're going to calculate the flux of this through the upper hemisphere. Which I'll write as H for hemisphere of radius r or radius r oriented outwardly. So outward orientation means that it's pointing away from the origin. So in particular, we have a formula for h if we want. These are all the set of points x, y, z, so that x squared, this is just the formula for the sphere, the full sphere. And we're going to take z to be non-negative. So we just take the upper half of it. This is a surface. So the solution, okay, let's talk about a solution to such a problem. There are two that we'll go over. One solution will be by computation. We'll use this formula that we just wrote down and compute this integral. Even in this case, though, we have to be cognizant of what we're doing. So, question. What do I need if I'm going to make this computation? Well, first, let's say what I'm computing. I want to compute the vector surface integral of this particular vector field F. I'm after this type of a thing for this domain and this vector field. So what should I do? What should I look for? Question to all of you. Any volunteers? I'm sorry? It's orientable. So good question is, do we have orientability? So that's maybe a first thing to make sure we can establish. So we do indeed have integrability here, or orientability, sorry, here, because we're looking at this upper half sphere, the hemisphere. And so we can certainly orient. And we're told that orient it outwardly. That means just orient everything to point away from the origin. So the full sphere is orientable. And therefore, any part of the full sphere will also be oriented. So we can indeed do that. Yes, it is oriented. And we've chosen an orientation. Other comments or questions or solutions? When you look at this formula here, after you're done vomiting, what do you think? Yeah. Right, so can we parameter, well, I'm just gonna say, yeah, we need a parametrization, right? We need a parametrization. Well, my memory goes back not very far, but I do remember last lecture. And I even have the notes from it. We did have a parametrization for a sphere of radius r. We did work, and I don't want to repeat it. So what we'll do is we'll copy it. I'm going to need this much of it. Now, last time, okay, Notability doesn't want to put it there. Last time, we parametrized the entire sphere. So what kind of changes do I need to make? First, I'll call this R, because the book, for whatever reason, calls it R. But okay, that's the only change in that notation. What else do I need to change? Am I parametrizing the whole sphere for this problem? No, I'm parametrizing the hemisphere, upper hemisphere. what else do I need to change? What do I need to change in this whole picture here? The bounds. Which bound in particular? Phi. What should I do with phi? Yes, I should go only to pi over 2 here. Thank you. That's great, guys. This should go to pi over 2, right? Because what are we doing here? This angle is phi, and phi stops once we get to a right angle. Right? If we kept on going, we would get something greater than pi over 2, but we don't want to be in that situation. So the only thing I need to change from the work we did last time is just that bound. Great. So now I look at that. I made a lot of the computations, and we can just go ahead and put those computations in. However, I want to ask you guys, can I use this formula? It's hard to kind of put it here. Let me just bring this in a little bit so I can get in the same page. So I want to use this formula. We had this definition. Let's recap what we did. We had this definition. I had a little discussion, and then I said, given that discussion, I get this formula. Can I use it in this case? What do you think? If we're at this point, say right here, right, this is x, y, z, right? Here phi is equal to pi over 2, theta equals 0. So let's put that into this guy here. At that point, this guy is what? Someone tell me. What's sine of pi over 2? Sine of pi over 2 is 1. What's cosine of theta? What's cosine of 0? 1. So what do I get here? I get negative r squared. Sine of 0 is 0. And cosine of pi over 2 is 0. So I get this. So my vector that I'm getting from this guy is pointing like that. Is that okay? No. It's not, I mean, it's okay. Life's all right. It's just, it's not oriented compatibly. This parametrization is orienting things opposite to the outward orientation. It's an inward orientation. That's something I need to note. It doesn't present a big problem. It just means that if you have an oppositely parametrized surface, you just need to put a negative sign in here. Because negative of that will be the right orientation. It's going to go the right direction. So what I want to do is I'm going to put that negative sign in, just artificially, into this formula. And that will then allow me to compute. So let's do that. Okay, I have everything I need. I'm going to go ahead and do it. I need to do f dot ds. It's going to equal the integral. Now I'm going from, well, I don't know which one. Let's go 0 to pi over 2, and then 0 to pi, 2 pi. And I'm going to do f. My vector field f is up here, but I noticed something about f. This is 1 over r cubed x, y, z. This is equal to f. Does everyone see that? The denominator here is r cubed. It's x squared plus y squared plus c squared square root. That's r cubed in each case. And I'm on the hemisphere of radius. I mean, on the hemisphere of radius r, capital R. So x, y, z, that is going to be x squared plus y squared plus z squared is going to be r squared. So I take that out just to simplify my notation. I'm going to dot that with this business. With my t, I'll write it this way. But now I need to put a negative sign. This is the wrong orientation. And I'm just going to write it this way. And here I'm going to write d phi, d theta. Okay. So I can pull out the negative 1 over r cubed. R is a constant. It's the radius of our hemisphere. And here I need to use my parametrization. X is equal to this, y is equal to this, and z is equal to this, just the spherical coordinates. So I get r cosine theta sine phi, r sine theta sine phi, r cosine theta, or cosine phi, pardon me. And here I'm going to dot with this guy, which is negative r squared, cosine theta sine squared phi, negative r squared sine theta sine phi, sine squared phi. Uh-oh. Oh, lost some pies there. And where was I? Yes, I'm doing t theta cross t phi. So I get minus r squared sine phi cosine phi. This is d phi d theta. Now you notice you can pull this r out of this whole thing, and you can pull a minus r squared out of this whole thing. And if I do that, I get a negative r cubed, and I can cancel with this leading term. So I will do that. And then I just have to do some multiplications. I'll have cosine squared theta sine to the cubed phi plus sine squared theta sine cubed phi plus sine squared phi cosine squared phi. Pardon me, I gave myself one too many signs here. Just sine phi cosine. Great, and this is d phi d theta. And again, you can see simplifications. Here we have a cosine squared plus sine squared. We can pull it out. If we do that, we get 1. So we get a double integral, 0 to pi, 0 to pi over 2 of sine cubed phi plus sine phi cosine squared phi. And again, you see that there's another simplification here. We can pull out we can pull out a sine phi, and we'll get a sine squared phi plus cosine squared phi. So this is just equal to a double integral, 0 to 2 pi, 0 to pi over 2 of sine phi d theta. Which, if you, this is not dependent on theta, so we get a 2 pi times the integral from 0 to pi over 2 of sine phi. And okay, this is going to be negative cosine phi, which is going to, if you look at the integral from 0 to pi over 2, sorry, this is dp. This is just 1. So this, I'll just let you can calculate. You get 2 pi. How did it feel? Feel good? Awful. It felt awful. People are walking out. Life is tough. It's hard being a Calc 3 teacher. Hey, but they missed out because there's another way. There's another way, better way. Conceptual. All right. Sometimes it pays to just ask some questions. Ask some basic questions. What is F? We actually saw what F was. F on this hemisphere, because we know on the hemisphere x squared plus y squared plus z squared equals r squared on the hemisphere. F is this. So let's write that down. F is 1 over r cubed. X, y. So that's another question. What about this outward pointing normal vector? Sure, once we wrote down the parametrization, we saw what it was. Kind of, we didn't even do the computation. We saw it's up to a negative scale. It's this nightmare that we had to work with. But what is n without all of that parametrization? Well, we had a drawing. It's just pointing directly out. Now, if I have a point here, x, y, z, how do I find the normal vector? I can take the line from the origin, right? Take the line from the origin and just continue from here to here. In other words, the vector is parallel to the vector, the normal vector is parallel to the vector x, y, z. Parallel and a positive multiple. And since we know it's a unit norm, we know exactly how to compute it. It's just the normalization of x, y, z. What is the norm of x, y, z? The vector x, y, z. Remember where we are. We're on the hemisphere of radius r. R. Cool. Okay, well, what is f dot n? What is f dot n? You guys can tell me. Remember, we're on the hemisphere. We're on the hemisphere of radius r. X, Y, Z, when I say we, I mean the point X, Y, Z is on that hemisphere. What is f dot n? Any guesses? 1 over r squared, very good. That's a correct guess. Let me just work it out. This is 1 over r cubed x, y, z dot 1 over r x, y, z. R is a number, right? R is a constant. It's not some variable. So I can bring that number, it's a positive number. So I can bring it out. I got 1 over r to the 4th. XYZ dot XYZ is x squared plus y squared plus z squared. But that's r squared. So canceling gives me 1 over r squared. And now what are we actually computing? Back when we defined the vector surface integral, before we went to that computational equation, we defined this as something. It is a scalar integral over f, or over h of f dot n ds. But we just found what f dot n is. It's 1 over r squared. And what is this? When you do a scalar integral of 1, you're computing the surface area of your surface. And we actually already computed the surface area of a sphere last time. And we got 4 pi r squared. Well, this is a hemisphere, so we cut it in 2. And we'll get 2 pi r squared. We're dividing by r squared. This is 2 pi. No spherical coordinates, no nasty cross product. So sometimes concepts pay off.